A high-speed rail modeled on the famous Shinkansen system has been chosen by the Taiwanese government to alleviate the serious traffic congestion that has developed in Taiwan. Private investors have been chosen to own and operate the system for a fixed period. The concession has been awarded to the Taiwan High-Speed Rail Corporation, and they have now embarked on building one of the world's largest infrastructure projects. Extending 345 kilometers from Taiwan's capital, Taipei, in the north to the industrial center of Kaohsiung in the far south, the structure is planned to be in operation by October 2005. Bilfinger Berger AG and Continental Engineering Corporation formed a joint venture, and they were successful in securing two contracts, C260 and C270, on a design and construct basis. These two adjoining lots are located in the center of the island and run for approximately 80 kilometers between the city of Taichung in the north and Jiayi to the south. Contract C260 starts just north of the city of Zhanghua, where the high-speed rail enters the Bagua Mountains. These are geologically young mountains that have been formed by folding and uplift. They are composed of dense to very dense gravel with lenses of sandy and clay silt. The general groundwater level is 10 meters below the invert of the tunnel. To traverse the variable terrain of the 14-kilometer route through this mountainous region, the alignment utilizes 7 tunnels, 13 bridges, and numerous earthwork sections. The Bagua Tunnel is the major element in this section, and at 7,364 meters long, it is the longest tunnel on the whole of the high-speed rail. Progressing south from the mountain region, the high-speed rail enters the western coastal plain of Taiwan. Competition for land on this plain is intense, as it is densely populated, heavily farmed, and dissected by innumerable local roads. For this reason, a continuous standard viaduct has been chosen for the alignment, as it has the least impact on the land. The Jiushui River is the boundary between contracts C260 and C270. The river is also approximately where the underlying soils change from the gravels and cobbles of C260 to the clay and sand of C270. The C270 section is 42 kilometers long and is constructed entirely of continuous viaducts. The viaduct is founded on cast in situ piles. The standard pile is 2 meters in diameter, and the JV used various methods of construction to suit the changing ground conditions. In the clay and sand of C270, the reverse circulation method was used. A drilling tool mixes the clay and sand with the drilling fluid. Suction pumps then remove the drilling fluid from the pile, and the suspended material is allowed to settle out in settlement ponds. Piles up to 65 meters deep were excavated using this method. Reinforcing cages were fabricated in 12-meter lengths by automatic machines. The cages were placed into the pile by crane and spliced to the final length. Concrete was placed by tremie pipe. In the gravels and cobbles of C260, the JV chose uncased drilling methods, utilizing large hydraulic rigs and sophisticated polymer drilling fluids. This technology had not been previously used in Taiwan, and the JV employed international piling subcontractors to undertake the work. 4 of the world's largest hydraulic rigs were imported for the task. Reinforcing and concrete were placed in the same manner as that used for the reverse circulation method. In the very north of the project, where the cobbles were too large to be removed by a drilling bucket, a small number of piles had to be constructed by the fully cased method. In total, the JV constructed 390,000 meters of piles. In the north of C260, where the ground is stiff, piles are not required, and large spread footings support the structure. Pile caps are used in all other areas where piles transfer the loads into the ground. The footing excavation was supported by sheet piles, and the reinforcing and concrete were placed in situ. For the construction of the columns and column heads, the JV tried to incorporate as much prefabrication as possible. The rebar cages for both components were assembled off-site and erected by crane. The formwork was also purpose-built and incorporated all the necessary access and safety requirements. These steps enabled the JV to achieve the production that was necessary to maintain the minimum of 1 kilometer of completed substructure in front of each substructure erection team. To withstand the large loads that are generated by Taiwan's severe earthquakes, the JV placed steel shear keys between the substructure and superstructure. Concrete shear keys are also used where access for maintenance is not possible at all times. To achieve the production needed, the JV chose the full-span precast method. For this method, the bridge superstructure is produced on a production line located in a precast yard. The precast yard must be located directly adjacent to the structure due to the restrictions in moving an 800-ton span. The JV established 2 precast yards, one on either project. The casting yards were fully self-contained and included all resources necessary to produce the spans, including batch plants and reinforcing cutting and bending workshops. The C260 casting line contained 3 molds, and 5 were used in C270. 880-ton gantries were constructed to handle the spans during production. The reinforcing cages for the spans are prefabricated in jigs and then lifted complete with the internal mold and placed in the outer mold. The concrete is poured, and after the initial concrete strength is achieved, the first stage stressing is carried out. The span is then removed from the mold and placed in the storage area. After the span reaches final strength, the stressing is completed and the tendons grouted. The span is now ready for transport. The JV produced 2 span lengths, 30 meters and 35 meters. The spans weighed 680 tons and 820 tons respectively, and a total of 1,958 were produced. The normal cycle was 2 days per span, and in peak production, 26 spans were produced each week. To move the spans, the JV commissioned the design and manufacture of special transport vehicles. The trucks were designed to handle both span lengths. They could carry up to 900 tons and traveled at 4 kilometers per hour under full load. For safety reasons, the trucks were automatically guided by an optical device that followed a line on the completed deck. The vehicle stopped immediately if it deviated from the line or the line was interrupted. Bilfinger Berger developed the concept for a new type of full-span launcher for this project. It introduced a front underbridge for faster launching and a smaller cantilever at the rear. The transporter delivers the span to the rear of the launcher, and the front winch attaches to the span. The span is moved forward with the load at the front carried by the winch, and the rear of the span supported on the transporter. When the rear end of the span is below the launcher, the load is transferred to the second winch. The span is then moved forward and lowered into its final position on the piers. The system proved very successful, and the JV cast and erected 1,958 bridge spans in 22 months. On one exceptional day, one launcher erected 5 spans in a 12-hour period. This series of time-exposed photographs demonstrates the erection sequence for 3 spans over a period of 2 days. In C260, the launching gantry had to be relocated 20 kilometers from the northern end of the viaduct to the south of the precast yard. The launcher's superstructure was supported on temporary towers, and the front and rear legs were removed. The main launcher body was placed on the span transporter and moved to the precast yard. Using the main gantries, the launcher was lifted off the deck and it was turned through 180 degrees. The launcher was then lifted back on the deck and reassembled. The total time to dismantle, transport, turn, and reassemble was only 13 days. Running concurrently with the erection of the superstructure is the construction of the deck finishing works. Most of this work was done in precast, so the number of activities to be done on site could be reduced. The only major activity that was cast in situ was the derailment wall. Another major finishing activity was the installation of the lockup devices. These provide the earthquake protection in the station areas and other non-standard sections of the superstructure. Emergency escape stairs and operations buildings were also constructed at many locations. Special or non-standard bridges were constructed in the Bagua Mountains, where the precast spans could not be used between the tunnels, and at other locations where obstructions were encountered that could not be spanned by the standard precast girder. A steel bridge with a main span of 85 meters was constructed over a main road. Incrementally launched bridges of up to 21 spans crossed valleys. Cast in situ concrete bridges with spans of up to 50 meters were used in many different locations. And balanced cantilever bridges passed over freeways and highways. In total, 130 spans of bridge structure were built by these non-precast methods. In the Bagua mountain region, large cuts and embankments were constructed where there was insufficient overburden to permit tunneling. In total, around 1,500,000 cubic meters of material was removed. To ensure the stiffness of the subgrade was consistent between the bridges, tunnels, and earthworks, 2.5 meter thickness of select subbase was placed in all cuts and embankments. Due to the very high rainfalls that are experienced in this area, it was important to install an effective slope protection system. A three-dimensional mat was secured to the slope, and this was sprayed over with a fibrous material containing plant and grass seed. Vegetation was therefore quickly established to protect the slopes. An important element of the C260 project is the construction of the tunnels. In total, 7 tunnels are within the scope of the project, and they have lengths ranging from 180 meters to 7,364 meters. The Bagua Tunnel is the longest of them and is also the longest tunnel on the entire project. The geology of the region consists mainly of compacted soil containing cobble, gravel, sand, silt, and clay. These ground conditions are ideally suited to soft ground tunneling techniques, so the new Austrian tunneling method, NATM, was adopted for excavation and temporary support work. Liebherr tunnel excavators are used to advance the top heading, and the excavated material is removed by loaders and articulated dump trucks. Lattice girders and mesh are placed, and then the temporary support measures are completed by the application of shotcrete up to 300 millimeters thick. In total, around 170,000 cubic meters of shotcrete has been placed. Bench and invert excavation follow the top heading. The same techniques of temporary support were used. However, there is less risk and faster advance rates can be used. A combination of the tunnel excavators and conventional excavators were used to excavate the bench and inverts. On the 29th of August 2002, the breakthrough of the Bagua Tunnel occurred. This was a major achievement on the project, as it marked the completion of the excavation of the longest tunnel on the project, and the occasion was marked by a celebration attended by the Premier of Taiwan, government ministers, executives from the corporation and partner companies, and many local dignitaries. The tunnels are provided with a permanent concrete inner lining to stabilize the structure and waterproof the tunnel for an indefinite period. After the PVC waterproofing membrane is placed, the lining is cast in 2 steps. The invert is cast first, and for this, the JV introduced a new method of having a twin invert form that allowed the casting of 2 invert sections at the one time. Each invert pour consumed approximately 180 cubic meters of concrete. The casting of the vault followed closely behind the invert. For this activity, the JV also introduced new technology that allowed 2 vault shutters to run in tandem and both be serviced by the one reinforcing wagon. The vault formwork was designed and manufactured in Europe and included all the latest technologies. The system proved to be very efficient, and each vault form was poured every day. In a construction period of 33 months, the JV completed and handed over 79 kilometers of guideway for the high-speed rail that included 67 kilometers of viaduct, 9 kilometers of tunnels, and 3 kilometers of earthwork. These works required the excavation of 4.8 million cubic meters of soil, the cutting, bending, and fixing of 520,000 tons of reinforcing, and the placing of 3.2 million cubic meters of concrete. While achieving these impressive productivities, the JV also produced a finished product of excellent quality, won 3 safety and 2 environmental awards, and handed over the works 2 months ahead of the contract date. The joint venture is very proud of these achievements and is pleased to have been able to contribute to the completion of such an ambitious infrastructure project.